Hi everyone, and welcome to this presentation called Automated Thread Evaluation of Various RISC-V Alternatives Using Random Instruction Generation. My name is Endri, and I'm a PhD student at Infineon Technologies, as well as Technische Universität Kaiserslautern in Germany. So I will first talk about the outline of this presentation. So I will begin with introduction, motivation, background. Then I will explain the RISC-V CPU generation, the model-based fault simulation framework, as well as random instruction generation. And in the end, I will conclude with application results, conclusion, and future work. So let's first start with introduction and motivation. As many of you know, the RISC-V is an open source instruction set architecture that is gaining a lot of traction in the recent years. The RISC-V is used in many applications, and more interestingly in AI, machine learning, safety, and security. But the focus of this presentation will be only the safety aspect of the RISC-V. ISO 26262, which is an international standard for functional safety of automotive, recommends fault injection to verify safety critical designs. The ISO 26262 has a risk classification system called ASIL, and it classifies different parts of the automotive, for the car, for example, into different safety levels. So the ASIL A would be the lowest risk safety level, and the ASIL D would be the highest risk, so safety critical of the car. So for example, the ASIL D would be the airbag, while ASIL A would be the rear lights, as can be shown in the figure. Safety critical designs can really endanger the human life, and so they require rigorous, stringent, and automated verification techniques. Most of the testing techniques are quite complex to achieve acceptable fault coverage, and moreover, it is required to improve the fault injection process to shorten the time to market deadlines. And that can be achieved by increasing automation, increasing productivity, and increasing performance. So let's move on with the background of this work, which would be the RTL generation framework, or named MetaRTL. The MetaRTL framework is based on meta modeling. So the specifications are formalized by being captured in a meta model. Then the template of design, which is a Python script, extracts this formalized specification and generates the model of design. The model of design has a tree-like data structure, and it is platform and technology independent hardware description. Then the APIs are utilized such that TOV, or the template of view, gets these data from the MOD and maps its elements to model of view elements. So the model of view, similar to MOD, is a tree-based, but is more language specific, more to the final layer, which would be the target code. The target code then is automatically generated by the framework, and it could be VHDL and Verilog. Now let's move on with a mixed register transfer and gate level fault injector. So the existing RTL generation framework, which I showed in a previous slide, is utilized to generate the RTL. After the RTL is generated, the synthesis is performed and the gate level netlist is generated. The TOD generator, which is a Python script, gets this data from the netlist, from the technology library, so the techlib, which the primary cells, as well as some input from the user, so which component is an object for fault injection, and generates a new TOD of mix RTL and gate level granularity, which would mean that, so let's assume that we have a design which we want to perform fault injection only on a multiplexer of this design. So what we would do is that the new TOD would represent this multiplexer only with primary gates, so just a logical gate like AND and ORs, instead of RTL primitives. So we would have a mix, and the rest of the design would be in RTL. So we would have a mix of RTL and gate level description of the design. Then the framework is utilized to generate the model of design. And as I said, the model of design has a tree-like data structure. So different operations can be utilized, like adding, deleting, or removing components. We get the data from the MOD, from fault collapsing to remove redundant faults. And then we add saboteurs to the existing desired fault location. So we would add some saboteurs, which are pieces of hardware which can inject a fault by having a control line. And we add these saboteurs to a desired location in the MOD. This whole process is called MOD transformation. Then the flow is utilized again to generate the RTL with sub-modules at gate level granularity plus saboteurs, which would mean mix RTL and gate level granularity. In the end, we perform the equivalence check to see if this whole transformation process has introduced any bug. The saboteurs control lines are, of course, constrained to not inject any fault. Now let's move on with the RISC-V CPU generation. As I said, the meta model is the key element of the meta RTL framework. And the meta model, which I'm showing in this slide, is this meta RISC-V meta model. This meta model is composed of 4 main components, which would be encoding root, exception, instructions, and architectural states. So the encoding tree defines parameters and the format of all the instructions. So here we can define not only RISC-V instruction, but a different kind of RISC instructions. The instruction component would describe the instruction and their behavior. The architectural states would represent the important state elements of the processor, such as program counter, GPR, or CSRs. And would be also the exception component, which represents, of course, exceptions, so unexpected events, and their behavior. Now let's move on with the model-based fault simulation framework. So the flow of the model-based fault simulation framework is as follows. So the meta-RTL is utilized to generate their design, which I explained in the previous slides. Then the fault injection framework transforms the design, which are generated by the meta-RTL, in a mixed gate-level RTL granularity. Then a script extracts information from this mixed RTL and gate-level granularity, and then generates the fault list. So all signals in the design which could inject a fault. And then the user configures the fault injection meta model accordingly. And in the end, the framework is utilized. So the fault simulation framework is utilized to generate system Verilog or C++ test bench. This is utilized for the very later in accordance with the model's data from the user. So in the next slide, I will talk about, so this is the model of the fault simulation framework. This model is composed of 3 main components, which would be the controller, or the simulation controller, the fault list, and the fault analyzer. So here the user can define what kind of fault injection technique or campaign he wants to utilize. An exhaustive fault injection campaign, which would inject all stacked faults at all design signals, at all fault list signals. Statistical fault injection, where the user can define a number of faults to inject or how many faults per simulation, as well as if the user wants to inject only a single event upset or only timing faults. And direct fault injection, where the user selects signals in the design where he wants to inject the fault. The fault list is automatically generated by reading the design, the mixed RTL and gate level granularity design, and then it generates the location, the saboteur control line, which controls the fault, as well as all possible fault models, which would be stacked 0, stacked 1, bit flip, and timing faults. Then, in the end, the fault analyzer, part of the meta model, This defines the signals that the user want to compare to the golden simulation. So the golden simulation would be the simulation where no fault is injected. So here the strobe, which is part of a group, then here it would be the signal that the user want to analyze. It could be primary output or in very important internal registers. The strobe type defines the output type, if it's the functional output or if it's a checker output of a safety mechanism. And this meta model is the one that the user configures in order to generate the fault injection campaign according to his wish. So in this slide, I'm showing a generated system Verilog test bench in order to inject a fault. So as I said in the previous slide, the user can define how many faults he wants to inject and how many faults per simulation. And line 3 represents the simulation count. So here would be the first fault injection. Then line 4 here defines a time point when the fault should be injected. So here it could, as you can see, could be the time point 50 and 52. So should be the clock cycle between 50 and 52. And since it's only for one clock cycle, it's supposed to be a bit flip. And here you could see that so this line 10 is actually triggering the fault control signal to inject a bit flip. And after this period is over, the signal value is restored to the original one. So there should not be injected any fault after this time point. So it's injecting a bit flip only for one clock cycle. And then this data is written into an output, a log file. And it's writing the time point when it is injected, and as well as what kind of fault model we are utilizing. And in this slide, I'm showing the output after we're simulating the previous test bench and design. So let's say we have different columns. So which simulation iteration it is, when the fault is injected, when the fault that we injected has propagated to selected strobes, so functional strobes or checker strobes. And here it's showing where the fault propagated at which strobe. So here it would be, which is on top SOC and would be the IB address out. And here we have the fault detection time. So if we would have a safety mechanism when the fault was detected by the safety mechanism. And here in the end, we would see which strobe of the safety mechanism detects a fault. And after the iterations are done, the faults are classified if they are detected or undetected by the safety mechanism, and the dangerous faults, which would be the ones that propagate to the primary outputs, and if they are detected or undetected by the safety mechanism. And in total, here in the end, it show the total amount of faults that we injected. So this is the output after our simulation of the generated test bench from the fault injection mechanism. So let's move on with the random instruction generator. So ATPGs, which are automatic test pattern generation, they provide adequate input test sequence to evaluate the dependability of safety critical designs. They are very common and provide very high fault coverage, but suffer from performance constraint due to long run times as well. ISO 262, as I mentioned before, it has different ASILs for different parts of the designs. Some parts could be ASIL B, ASIL A, or ASIL D. And thus, we do not need to have very high fault coverage for every part of the design. So it's possible to combine model-driven fault simulation framework, which I explained before, with a model-driven random RISC-V instruction generation. The key element of random instruction generation is the RISC-V meta model, which I explained in slide 7. A Python script reads that model, so the model would be the data filled by the user, and generates a random valid instructions. And it's highly configurable, which has the constraints, so the user can constrain the class of the instruction to generate. It has the length, so the user can specify the number of instructions to generate, the file type. Until now, we're supporting hex and binary files, and memory start address, so the user can specify the start address of the data memory. And then by utilizing this random instruction generation and the model-based fault injection framework, as I explained in the previous slide, we're doing fault simulation campaigns on a CPU subsystem. So the random instructions which are generated are utilized as a test input for the RISC-V CPU. And the CPU subsystem is composed of program and data memory instances, CPU itself, and different peripherals such as SPI, UART, interrupt controller, and bus bridges. The tests are run on 3 similar subsystems with different RISC-V alternatives, which means that we're using the same subsystem, so the same memories, same peripherals, but we're changing only the CPU. And faults are injected only on interesting components like ALU, forwarding unit, prefetcher, and fetch stage. So only these components are kept on a gate level, and the rest of design is kept on RTL, because we're using our mix RTL and gate level granularity framework. In this slide, I'm showing the results when we apply the faults on the RV32 IMC, so this is RISC-V specification. We're supporting IMC instructions. And we're injecting these manifolds on ALU, forwarding unit, prefetcher, and fetch stage. As you can see from the chart, the increase, so we're at first, we executed only 100 instructions, and we got a low fault coverage rate when it comes to the prefetcher and fetch stage. And then by increasing by 50, the fault coverage increases, and the steepest incline could be seen on the prefetcher. And then start to saturate after 250 instructions. For the forwarding unit, we got 99% fault coverage when we executed 300 random instructions. And we got the lowest one for the fetch stage. Then what we did is that we also added support for the exceptions, so RV32 IMC X. Then, since the exception unit is added to the fetch stage, the amount of the fault to inject would be quite higher. Similarly, we got very similar results like before, only with a slight increase for almost every component. And then we apply the fault injection again to RV32 IMC MAC. Similarly, we got again similar results like previously, only with an increase, a very slight increase of 1 to 2% of fault coverage. And then what we did is that we applied the statistical fault injection campaign. So in this case, like the previous campaigns, we are not injecting only stacked faults, but we are also injecting bit flips as well. And all of the faults that we are injecting are random. And then here you could see the result. And for all components, we did 300 instructions as test length. And we injected only 30% of the total amount of faults. And here you could see for all components, according to SFI campaign, the fault coverage is lower than for the stacked faults. And the fetch stage, as could be seen, had the lowest fault coverage rate. So let's conclude. and give an outlook for future work. So the low overhead automated safety evaluation of various RISC-V alternatives by combining model-driven fault simulation and model-driven random instruction generation. The exhaustive fault injection campaign resulted in an acceptable fault coverage range, so starting from 40% to 99% for length of input test of 300 instructions. And since the flow is automated, the total effort was quite low, so just 1 person day, and mostly was spent on configuring the model. And as an outlook for future work, we thinking to extend the supported fault models to constrain jumps to outbound memory locations and further comparison to other commercial and open source fault simulation tools. Thank you for your attention. And if you have any question, please let me know.